and we'll be ready to launch into on Thursday, getting SPSS all downloaded, getting you set up to do an in-class assignment, and getting that done on Thursday. Okay, so here we go. We are going to talk to you today then about some of the descriptive statistics that I was referencing when we were telling the difference between statistics and parameters. All right, so the first way of describing, oh, well, my stupid joke just went on its own. Dang it. All right. The first way of describing a group of values in a data set, okay? A frequency distribution is one of them. That's the visual representation. But sometimes what we really like to do is to take the entirety of a data set, the entirety of the different representations, the different measurements of one variable, and express them in terms of one representative value. Okay, the one number or the one name that does the best job of standing in for the entire data set as a whole. And that's what we call a measure of central tendency. Okay, so central tendency is the search for the most representative value in your data set. We're going to talk briefly about 3 of them, and then we're going to almost relentlessly stick to only one for the rest of the class. But those 3 measures of central tendency are mean, I hope you get it, the median, look, Google image search-based humor is some of the lowest form of humor, but it's really all I got right now, okay? There's also the mode, a la mode, or there she is back. Okay, that was my joke, the Edna mode. But let's talk about it. All right, so the first thing that, and the most useful measure of central tendency that we are going to use in this class is the mean. Now, mean is a relatively precise term. Arithmetic mean is the most precise term. What the mean is usually meant to convey is this thing that people talk about when they say average. But average isn't a precise term. Okay, mean is the precise term, and arithmetic mean is the most precise term. There are other kinds of means out there. You may have heard of them. There's the geometric mean. There is the harmonic mean. There are other ways to get a mean, but we're going to do the arithmetic mean. One thing about the arithmetic mean is that the arithmetic mean is only for use with interval and ratio data. That is because the first thing that you do when you're calculating an arithmetic mean is sum up all of the x values in your data set. All right, here's the formula for the mean that we tend to use. The symbol for the mean is x bar, x being all the things that you are concerned with in your data set. Your data set is made up of x's. There's the first observation you had, that's x sub 1. There's the second observation you had, that's x sub 2. The third, you get it. When you put them all together and then take an average, you're getting that line means arithmetic mean. And then what it is that you average together was a bunch of x's. So that's why it's an x bar. The formula for x bar is this. You sum up all the x's in your data set, and then you divide by the number of different values in your data set. That's n. So even though you know how to do an arithmetic mean, you're not going to need to reference this formula in order to figure it out. Okay, I don't think you're that in need of guidance. But it's a good way to remember what sigma means. Sigma means add up all the different values for that variable, and then what n means, the number of values in your data set. Okay, sorry that I had a little bit of an issue here with placement, but that is an x bar right there, and x bar equals the mean of your sample. That means that it is a statistic. It is a statistic. It is a description of your sample. Therefore, a descriptive statistic. It is partners with, its analog in the population space is the parameter mu. So mu and x bar have a relationship to each other. They're not going to be precisely exact, but mu is the actual real average of an infinite number of observations in which all of the noise and error cancels each other out to get the real true value. An X bar is basically the same thing, only for a smaller group of numbers that you've actually managed to gather, your sample. And it should look a lot like mu, but it isn't guaranteed to be precisely mu because there is going to be error in the X bar term. All right. The thing about means, the only reason that they have a drawback is that, well, first, they can't be used with categorical, that is to say nominal or ordinal data. But the other thing is, even when you're working with interval and ratio data, there are times when the mean is not as useful as it could be. And that's because of this. Means are very sensitive to values, rare values that are far away from typical, right? So let's say that I had this, like these 4 numbers were a data set. These were 4 different observations of some variable. And I had 3 that were down here that were fairly low, that were giving you a story that this is typical of measuring that variable. But I had 1 value that was way over here, single, rare. We're not sure why it's over there. It could be a measurement error. It could be just a rare value that's very large. But that 1 rare large value is going to pull the mean as a measure of central tendency above what is clearly typical of measuring this variable. All right. So they're sensitive to outliers. They get pulled in one direction or another by rare but extreme values. That's why when you get into more advanced statistics, you might every once in a while check a data set to see if the mean is even an appropriate measure of central tendency for that data set. If there are too many or too extreme values, people start losing faith in the mean as a way of expressing a typical value in a data set. That's why in those situations, it's often a good idea to fall back on another measure of central tendency called the median. The median is useful for 2 reasons. You can use the median with ordinal data. All right. If all you have is how people rank, but you don't know how far apart from each other they are on some measure, the median will work for you because you will still be able to know, given their ranks, who is in the middle. And that's what the median is all about. The median says, what is your middlemost value? And so that means half of the values are below it and half of the values are above it. You can do this with interval data, ratio data, and also ordinal data. Now, there's a formula associated with this, and it trips people up sometimes. But this formula, n+1, and then divide that number by 2, will not give you the value for the median. All right. If you do get the value for the median, that was an extraordinary coincidence and you got very, very lucky. But this is the positional formula. This tells you if you put all of your values in order, which position would be the one where the median was sitting. All right. So let's say this is my example here. I have 1, 2, 3, 4, 5 data points. The median will be determined by the value of the data point in the 3rd most position. Right? That's why if you put it into the formula, I have n, 5 data points, plus 1 is 6. 6 divided by 2 is 3. My median is going to be in the 3rd position. So whatever this number is right here, that's the median. All right? Now, the nice thing about this is that the precise values, extreme or not, of almost all the values in the data set don't actually matter. All right. It doesn't matter how far above the other data points a particular data point is. It is simply one data point that is on top, that is at the top. All right. The only data point that actually determines what the value of the median is the data point that is in the middle of the data set. You will see the median used in real life situations where it's typical that there are going to be extreme outliers in the value. And one of those is real estate. So whenever anybody talks about what a typical price is for a home in an area, they are never going to talk about mean home price. Or if they do, they've got an agenda that they're trying to fool you with. What you always hear when you're talking about real estate is median home price. And the reason for that is when you're in real estate, the bulk of typical dwellings in an area are going to be the ones that are cheapest. Okay? The most plentiful housing in an area is also going to be the stuff that's cheapest. So you might have a building full of apartments, single bedroom. Rarer might be 2-bedroom, rarer still might be 3-bedroom, then maybe some townhomes, some single family standalone houses. But somewhere in that zip code, there is bound to be like 1 or 2 people who have homes that you can't even see from the road, right? You know, those ones where you're like, you don't even know that there's a beautiful house there because it's so big and so beautiful that there are like trees and a forest. And you have to drive back to even get to the 15-bedroom mansion with the private lake and the horse farm, right? Okay, that's like a $15 million house. Well, shoot, if you went asking what is the average or mean value of the housing in that area, it's going to be like 300 single-bedroom apartments, maybe 200 houses, and this one $15 million property that is worth as much as all the apartments. That wouldn't give you a representative value. So what you actually do is take the median. What is the house at which half of the properties are less expensive and half the properties are more expensive? Under those constraints, one horse farm is worth just as much as one-bedroom apartment in terms of moving the typical value around. All right. So, and by the way, I need to point out that the formula I gave you kind of has a cheat in it. That cheat is that it pretty much only works for data sets with an odd number of data points. So I'm going to have to go ahead and give you a workaround if you end up with a data set that has an even number of data points. Because, of course, if you had something like 8 data points, 8 plus 1 is 9. 9 divided by 2 is 4.5. Well, you don't have a 4.5 data point. But in that case, you would take the arithmetic mean, falling back on the mean, of the 4th and 5th points, get the middlemost value, and call that your median. All right. Lastly, the last measure of central tendency is the mode. The nice thing about the mode is that you can use it for any level of measurement. The only thing that the mode is about is the most common value, the most frequently occurring value in the data set. So even if you're doing nothing more than assigning people to categories that have a name, you can still tell which category has the most people in it, and that's your mode. If you're looking at a frequency histogram, the mode is always going to be the tallest spot. All right, so easy to spot on a frequency histogram, not a terribly complicated concept. So let me just go ahead and give you a chance to limber up the fingers in the chat here before we move on to more complicated things. If this little data set here, 1, 2, 3, 4, 5, 6, 7, 8, 9, this 10-number data set was the data set that you were using, its values are 3, 5, 17, 4, 3, 18, 19, 1, 17, and 3. What is going to be the mode of that data set? Excellent. Okay, so that makes a consensus. Yes, the mode is going to be 3. 3 occurs 3 times. That's just a coincidence. 17 occurs twice, but 3 is more than that. Now, that's going to be a weird way to say the typical value for this data set because 3 is one of the lowest values in the data set, but nevertheless, it's the most frequently occurring one. And so if you were using mode for a measure of central tendency, you'd come up with the answer 3. Just in case you didn't catch this, if you are working with nominal data, the mode is your only option to describe a measure of central tendency. You can't do medians, you can't do means. The mode is all you got. All right, that's the simple stuff. Here we're going to get a little bit more complicated. Another descriptive statistic that we are interested in when we're looking at a data set is not just what is the single most representative value, but once you have that value, how much do values in the data set tend to differ from that representative value? Another way of asking is that a good representative? Does the whole data set agree that this number that is a measure of central tendency is a good representative to send to represent the entire data set? Okay, so this idea then is one of variability or dispersion or spread. Now those make up the in air quotes at the top of the slide because those are 3 general terms that are standing in for this concept. And I want to be very careful about how I use the terms, because sometimes a term that we think is precise is not, and sometimes a term that we think is general is precise. So variability, dispersion, or spread are three words that stand for this whole concept. How spread out are my data points? Other things are going to be more specific, all right? Especially variance. I'm using variability here, but not variance. Variance is a specific way to measure this concept. But before we even get there, I'll tell you about an easy way to measure variability, and that is simply the range. Okay, what is the lowest point in your data set and what is the highest point in your data set? Okay, what is the smallest value and what is the biggest value? That will give you your range. That will give you some idea as to what kind of field of possibilities you are looking at. All right. So for example, when you look at the weather, it'll give you a predicted low and a predicted high for that day. That is a range of anticipated temperature, right? So if anybody asks you, hey, what's the range going to be on temperature today? You would say, and here's the format that I'd like to use for this class, parentheses, put your lowest value, give me a comma, give me your highest value, and then put another parentheses. That's how we're expressing range. All right. Please do not, and this is going to be tricky for some people as well, please do not express that range as a single number that is the difference between the top and bottom number. So in this case, the proper answer for what's the range of temperature is not going to be 17 degrees. And the reason for that is this, and this is also going to get into our significant figures talk. But when you express a value of 90 degrees in temperature, what you're actually expressing is, I would have said 90 degrees if the temperature was anywhere in between 89.5 and 90.5. Any value in that entire range would have been expressed as a 90. So you've actually got a half a degree above 90 that is a part of this range. Same thing for 73. You've got a half a degree below 73 that is also a part of that range. So technically, if you were really going to do this precisely, the range expressed by the difference between 73 degrees and 90 degrees would actually be not 17, but 18 degrees. That's why I'm asking us not to even bother with it, because I don't want to go into trying to figure out the difference between continuous and categorical or real limits, or all these variables. Just give me the low number and the high number. All right. The next thing that we're going to do is talk about not just how spread out the field is in terms of its lowest and highest number, but within that field, how are the numbers distributed? Okay. If you have a really big, if you have a range of any kind, it's entirely possible that all the values except for two are right in the middle, but you have one extreme outlier on the left, one extreme outlier on the right, and they're determining the range. The other possibility is that you would have something like what's called a bimodal distribution, where there's a whole lot of values on the left and there's a whole lot of values on the right, and almost nobody's in the middle. We want to have some number that would give us an idea about what kind of distribution we're actually looking at, instead of just having a range. Okay, so what we're going to do with this is try to get some sort of agreed upon expression of how much a number typically, or value typically, wanders off from the measure of central tendency that we've expressed for that data set, okay? Or some sort of benchmark for that data set. Now, we're going to go ahead and use the mean. And the reason we're going to use the mean is because if you use any other number, you end up running out of utility for this expression as you try to go on and on and on and doing more and more with it in statistics. So just for practicality, starting by saying, you know what, the benchmark value that we're going to start measuring distance from to express this number is the mean. But there's no mathematical or philosophical reason that you couldn't have used the median, or that you couldn't have used the mode, or that you couldn't have used 0, or the bottom of the range, or the top of the range, or anything like that. It just so happens that when you use the mean, you end up with a process that gives you a really useful number. That number, and I'll give it away right now, is the standard deviation. So what we're going to do here for the next few slides is to tell you how and why we end up with the standard deviation as the most useful expression of dispersion, spread, or variability in a data set. Okay? All right, so we start with the mean. You have to calculate it. This, by the way, automatically eliminates nominal and ordinal level measurements from the standard deviation. That's why we are almost always going to have something that is interval or ratio in our data set, because one of the first things we're going to want to do is get a mean and then get a standard deviation. All right? That's why we need interval or ratio data. So the first thing, calculate your mean. The second thing, just to make things easier on yourself, put your values in order. Start with the lowest, go up to the highest. That will keep you working a pattern of increasing and decreasing numbers when you start working with their distance from the mean. That will make it clear to you quickly if you've run into an error. All right. Mathematically, you don't have to do this, but when you're working it by hand, it makes things easier. The next thing you want to do is get the difference between every single one of the values in your data set and the mean that you have calculated. You can either subtract the mean from your values or subtract your values from the mean. It doesn't matter. And I'll show you why. Now, here's the thing. This is going to get really complicated if I keep trying to talk about it in the hypothetical. So we're going to walk through the rest of the steps using a data set. This is a data set. It has 3 numbers. They are very small. They are very simple. This is Sesame Street stuff. 2, 3, and 7 are going to make up our data set. All right. I asked one person, how many apples do you have? And they said 2. Somebody else said 3, and somebody else said 7. Right. 2, 3, and 7 apples. Got it? You got it. So the first thing we do with this data set, by virtue of the fact that it is interval ratio data, is add them all up, get 12. 7, 3, and 2, and then divide it by n, the number of numbers in the data set. So 12 divided by 3 gives us 4. So our x bar, our descriptive statistic for the arithmetic mean for the data set 237 is 4. Man, I'm good. I'm looking at these whole numbers. Whole numbers are great. Whole numbers are going to work for us. All right. Now, I said the next thing you do is you collect information about how each number in your data set differs from that measure of central tendency. So in this case, I'm going to subtract the mean from all of my numbers and get a new set of 3 numbers that are differences. So 2 minus the mean is -2. 3 minus the mean is -1. 7 minus the mean is 3. So I have a difference of -2, a difference of -1, and a difference of 3. All right? Now, I don't want 3 numbers. I already had 3 numbers. What I want is one number that expresses how do values typically differ from the measure of central tendency that we're working with. All right. Well, up to this point, any time that we have looked for a representative value for a data set, we've gone for the mean. Right? So we could say, what's the mean of -2, -1, and 3? First step in the mean is to add them all up. And look at that. -2, -1, and 3 gives us 0. 0 divided by 3 also gives us 0. So if we averaged all these deviations, we are going to be trying to make the case that the typical amount that 2, 3, and 7 differ from 4 is 0. We will be stuck with the illogical stance that there's no difference at all between 2, 3, 4, and 7. That's not where we want to go. That doesn't work. That's not true. Now, I'm going to tell you, this procedure fails every time, no matter what numbers you had in front of you. It is one of the properties, the mathematical, undisputable, every time properties of the mean, that if you took all the deviations from the mean, from the numbers that added up to give you that mean, and then you add those deviations up, you'll get 0 every time. Okay, doesn't matter how complicated the numbers are, doesn't matter how big the data set is. If you get a mean from a data set and then you add up all the deviations, positive and negative, you're going to get a sum of 0. That's what one of the things it means to have a mean. So we got to get around this. We got to figure out a typical value for how much these things deviate, but adding up these values is going to give us 0 every time. What can we do in order to get around this problem, this dilemma? Give me a suggestion. Excellent idea. Okay. So what we've always been interested in really is not whether these values are on the left or on the right on the number line, but the raw amount of distance between these numbers and the mean. So we could say, you know what, forget negatives, ignore negatives. Let's just take the absolute value of these numbers and then make a mean out of that. Okay. Now that would be something that we could do. Would be useful. By the way, Rachel, I appreciate the chiming in. If we took the absolute value of that mean, though, we'd be taking the absolute value of 0. So we need to take the absolute value of the values first and then make a mean out of them. Am I being pedantic? Am I being picky? Absolutely. In real life, I'd be a jerk for pointing that out. Maybe I am a jerk. But in these things, in math, if it's going to make such a huge difference in your final answer, it's worth pointing out that the order in which you do things makes a big difference. So let's say that we did that. We could then take the absolute value of -2, the absolute value of 1, the absolute value of 3, and add them all up. We'd get what? 7. And then take the average of that, 7 divided by 3. All right, so we get like 2.5. That would be a thing that we can do. Mathematically, there's no reason that that's a bad thing. Okay, that would give us something that mathematicians have a name for. That would be the average deviation. Turns out, for reasons that don't come clear until way on down the line, average deviation doesn't do as good of a job of describing things like normal curves and other really useful frequency distributions as it could. Okay, so an average deviation is a thing. There's nothing wrong with it, but it turns out not to have a lot of utility. So we're going to take a step back and figure out another way to deal with these negatives that sum up to 0. Is there any other way you know to take a number and get rid of a negative? Yes. Thank you. Maggie says square it. Anytime you square a number, you get a positive value. Negative times a negative gives you a positive, and a positive times a positive gives you a positive. So we can get rid of the negatives that are causing us a problem here by squaring every value before we go on to do our next step. And that is exactly what we do here. Okay? Square those values, and then we can start looking for something that looks like an average. All right? So squaring those values and then adding them up gives you a step in this procedure that actually has a special name. It is called the sum of squares. It's one of those names that actually makes sense. It's one of those names that I would have chosen if I was trying to make things easy for you. Okay, it doesn't happen all the time. Appreciate it when it does. So sum of squares is when you take all of the different scores, you square them, and you sum them up. This is a step in our standard deviation calculation. It is also a step in the calculation of what I'm going to label and flag for you is called variance. But despite the fact that your book and its chapter talking about this stuff doesn't flag this as having a special name or call it anything, I'm going to call it sum of squares because we're going to run into this concept a few weeks down the road when we start doing different things, and I want you to know that you're already familiar with it. Okay? So in our little toy example, we had our different scores over here, negatives and positives, but we square them, we get -2 times -2 is 4, -1 times -1 is 1, 3 times 3 is 9. Now we have our squared values here, summing them up gives us 14. That was the application of this formula here. Okay? Just to refamiliarize you with how we note this. When you have a sigma, what you're basically asking is to carry out whatever procedure is to the right of the sigma for every value of x that you have, and then add those results together. It is important to get these done in the correct order, okay? You don't want to subtract, take x minus x bar and then add it to x minus x bar and add it to x minus x bar and then square it at the end. You want to do this entire procedure for every x before you add it to the next procedure for the next x. Right? Important stuff. But there we go. That is the sum of squares formula. Its abbreviation in other lessons will be S and S for sum of squares. And the answer here is 14. Okay. Now we need to check in. Is 14 a useful expression that would give people the right idea about how much 2, 3, and 7 typically deviate from 4? The correct answer is no. 14 is way too big of a number. Something has to be done. One of the problems with the sum of squares is that it does not take into account how much information you put into the system. We're trying to get a typical value, but the sum of squares is the sum of the values. All right, so here's my little example here. I have a data set that is 5, 6, 7, 8, 9. 5 values in it. Very easy. The average here is 7. The mean is 7. Okay. And if I did a sum of squares for this little data set here, I would have 5 minus 7 is negative 2, squared is 4. 6 minus 7 is negative 1, squared is 1. 7 minus 7 is 0. 8 minus 7 is 1, squared is 1. 9 minus 7 is 2, squared is 4. So I'd have 4 plus 1 plus 0 plus 1 plus 4. And the sum of squares for this little data set would be 10. Okay, no problem. But take a look at the data set below it. I hope nobody would really seriously argue that the data set here has more variability or is more spread out or is more diverse than the top data set. There just happen to be twice as many values in it, but they are spread out in the exact same way over the exact same range. They're just more dense. But nevertheless, if you did a sum of squares for this 10 value data set, you would get 20, because everything that I did up here, I'm doing it twice down here. So like many things, when you're trying to get a typical value, you have to take into account how many values went into the sum. So in order to cut the sum of squares back down to size by taking into account how many values went into the sum of squares, what do you think we ought to do? Removing duplicate numbers would make these two sums of squares match up together. Absolutely right. I hate to lose data though. And the funny thing is, if I have a duplicate number, it probably means something valuable in a typical sense in a data set, that value comes up a lot. And if it comes up a lot, I want to record and appreciate and make use of the fact that I know that value comes up a lot. I don't want to only take one value if value would duplicate itself. Dividing by the number of data points, dividing by n. That's typically what we do. When we get an arithmetic mean, that's our next step, right? We add all the values together, we divide it by n, and now we have a typical value. So let's do the equivalent here with our sum of squares. When you do this, you get that thing that I said has a special name. This is what the variance is. Variance is the average value you get back out when you do a sum of squares. So variance is like the average squared value, okay? Another word for variance when we get to ANOVA is mean square, and that makes sense. So the formula here is to take sum of squares and put it over n minus 1. Niehaus, you might say. What? Because where'd that 1 come from? You can't just throw random numbers into a formula and expect that we'll just take your word for it, because you didn't explain where that 1 came from. When we do a mean, we divide by n. So why did we sum everything up here and then divide by n minus 1? What are you doing? This is one of, I think, maybe only 3 or 4 times in the class when I'm going to just ask you to make something a part of your procedure, make it a process, without taking the time to explain it all the way down as to why it happens. This is going to be one of those you're just going to have to trust me moments, and I have a special meme for it. Okay? This is one that I'm just going to have to ask you to take on authority or take on faith. There's a reason to do it. And without going too far into it, because as I said, I don't like mathematical tangents, but using n minus 1, also known as degrees of freedom, keeps you on track to properly and in an unbiased way give the proper expression for the deviation at the end of the process. If you just use n instead of n minus 1, you would systematically underestimate how much variability there is in the data set. Okay. I'm not exactly sure precisely why, but the correction for this process to give you the right answer at the end that is most useful is to slip an n minus 1 in there when you're going between sum of squares and variance, right? So doing this to our data set gives us the sum of squares divided by n minus 1, which is now the sum of squares divided by 2, which is 7. Our mean squared value is 7. Is 7 what we're after? Is 7 a good way of expressing the typical amount that our numbers deviate from 4? Still not. It's still not. And the problem we still have with this value is a little bit expressed in the name. It is the average squared value. What do you do when you have a squared value, but you don't want a squared value? You want a regular value. That's it. So in order to correct back for the correction we made to work around our problem of everything summing to 0 in the first place, we have to undo that here at the end by taking the square root. And that's exactly what we do, right? So in order to take a mean squared value and get it back to basically just a mean value, we take the square root. So our mean square, our variance was 7, take the square root, and we will have the actual standard deviation. Standard deviation is where we have ended up, okay? The square root of 7, 2.65, gives us a reasonable value for how much 2, 3, and 7 deviate from 4. The biggest deviation was 3. The smallest deviation was 1. Somewhere between 1 and 3 is where our answer should be. The square root of 7, 2.65, fits nicely in that window, and so we are done with that procedure. Standard deviation is such a useful and common number to use that it has the honor of getting its own symbol, right? If you're talking about a population, a parameter, that symbol is a lowercase sigma. That's the Greek S. It's written like this right here, like looks like a little O with a hat on it, right? That is a parameter sigma. You'll never calculate it, because if you were trying to calculate a sigma, you'd have to work with an infinitely large data set, and we don't do that sort of thing around here, all right? So if you ever have a sigma in a problem, it's because I have given it to you as a part of the setup of the problem. Now, what we have just done here with our data set is actually gotten the descriptive statistic S, the standard deviation of the sample. That is written in a regular English Arabic letter that we all recognize, but that is merely a description of your sample, not a description of the larger population level phenomenon. So we've calculated an S. If we ever want to talk about variance again, which we will, which we might again, what we actually do is express that as the squared value of the standard deviation. The reason we do that, the reason that's the convention, is because standard deviation is the most useful number, variance is the second most useful number, or the less useful number, and so we make that expression more complicated. It would have made perfect mathematical sense to have given variance the symbol that stands alone, like a V or something, and we called standard deviation the square root of V. But since we're usually most interested in the standard deviation, we express it such that variance is the squared value of the standard deviation instead of the standard deviation being the square root of the variance, even though they are both technically true. Okay? So now we've got our typical expression of how much a value in a data set tends to differ from a measure of central tendency. That is standard deviation. Here is the entire formula altogether. Let us take a look at that and use it to refamiliarize ourselves with how these formulas are expressed. Starting off here at the top, this is a sum of every x minus the mean squared and then added to the next one, added to the next one, added to the next one. People sometimes get confused on this. They're like, wait, what's x again? What value is x? X has as many different values as there are values in your data set. And you're going to do this procedure once for every one of those values. X bar is going to stay the same every time because you're always working with the same average for the data set. You to get that difference, you square it before you put it in. There are n number of x's. So x has a relationship to n in that n is the number of x's that there are in your data set. It's typically expressed like this: x sub 1, x sub 2, dot, 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 x sub n. X sub n is always the last value in your data set because you've hit the number of values that you have. Okay. If I wanted to be more specific on this, I would give the notation below and above the sigma that tells you when to start and when to stop. But that's usually not necessary for people to do these equations. And so to keep it simple and less messy, I express it like this. All right. If you did all that, you would have the sum of squares sitting in the numerator up here. And then you divide it by n minus 1 to make the entire expression within this square root the variance. Here's something that trips people up sometimes when they are writing quickly or taking messy notes or just working on their own. Sometimes they forget how deep the square root symbol dips in this formula. This square root symbol dips all the way to the bottom, encompassing everything that is underneath it. People will get the wrong answer for the standard deviation if they do something like forget and dip the square root only down to the bottom of the numerator. In that case, what they do is they would get the sum of squares, they'd take the square root of it, and then they divide by n minus 1. Totally wrong answer. Taking the square root is supposed to be the last thing you do, so please make sure that it square roots or encompasses the entire expression underneath it here. All right? So there we go. In our example, our 2, 3, 7 data set became -2, -1, and 3 for different scores. The squared values are 4, 1, and 9. They summed up to 14, the sum of squares. Putting it over n minus 1 gave us 7 for the variance, and the square root of 7 gave us 2.65 for the standard deviation. Now, there's a subscript with this standard deviation. It wouldn't be necessary if this was the only standard deviation that we were going to do, but it's time to start labeling things so that it is clear when things get more complicated what we're dealing with. This has a subscript of an x. And the reason it is subscripted with an x is to keep track of what the raw material was that went into this equation, that went into this formula to give us a standard deviation. The subscript answers the question, standard deviation of what? Standard deviation of a collection of individual measurements. Standard deviation of a bunch of x's. That's why it has a x subscript. Other possibilities when we get down the line are going to be things like x bars. If we had a group of numbers, each one of which was itself an average, and we took a standard deviation of those averages, the subscript would be x bar. It'd be s sub x bar. We can do differences. We can do averages. We can do ranges. We can do anything. right now, what I'm telling you is that we put a bunch of X's into the machine to crank out a standard deviation. Therefore, it's S sub X. Does that make sense to everyone? Why we've subscripted it that way?
Professor, I'm sort of just so I understand why we did that.
Okay.
But where I'm confused is I thought it was SS. Did we just I don't know, I think I just confused myself.
SS was the symbol for the sum of squares.
Which was 14.
So that was, yes.
Okay.
Sum of squares was 14. That's just a special label for one point in this process.
Okay.
The process ended when we got to standard deviation. This lowercase s here stands for standard deviation. Those two S's stood for sum of squares.
Okay. Okay. I understand now. It's
there we go.
Finished.
There we go. Yeah.
Thank you.
Yes, and they were different things.
Okay.
It will not always be S sub X, but it will be S sub X as long as you're dealing with raw data. When you're dealing with the raw observations that you have, each one of those observations is an X, and we will then say S sub X. If the question is, will it ever be like S sub B or S sub U? No, unless that's what we're calling every instance of observation in our raw data. Okay, but typically that kind of variable is an X when we start. The only exception to that will be when we do regression at the very end of the class. In that case, we're actually going to have two continuous variables. One is the X variable and one is the Y variable. In that case, we'll have Y sub 1, Y sub 2, Y sub 3, and the standard deviation of those numbers is going to be S sub Y. But that doesn't come up for another, I think, 9 weeks. Okay, right now we're going to be dealing with a bunch of X's as the starting point for dealing with data sets. If that's what the question was.
Oh yeah, that makes perfect sense now. Yeah, thank you so much.
Okay, cool. All right, then let's see what else we had to go here. Here's then the recap. The standard deviation is done by ordering your data, putting it in increasing or decreasing order, getting the mean, finding the difference between each data point and the mean, taking those values and squaring each one, adding them up to get a sum of squares, dividing them by n-1 to get a variance, and then taking the square root to get a standard deviation. I have full faith that if this was all you had to memorize for the semester, you would not have a problem doing it. I wouldn't need to make a cheat sheet. I wouldn't need to make a summary sheet. You could get this. But this is just the first example of a step-by-step procedure that is going to be joined by a lot of other procedures over the course of the semester. And sometimes they vary from each other in weird and subtle ways that it's hard to keep straight. So standard deviation is then the first procedure that has its own standalone explanation recap page in the packet that I sent to you by PDF before we started the class. That's the format that I'm going to use no matter how long, complicated, and confusing a process is when we get into starting to do hypothesis tests on down the line. Okay, so I've got a page like this for standard deviation, but I've got to have a page like this for t-test, a page like this for ANOVA, a page like this for regression, a page like this for chi-square. All right, but this is just the first one. Now, good. And again, that packet, it contains, I suppose, all the information from your textbook that you would technically need to do if you were a perfect robot with a perfect memory to pass this class. But the thing that is missing from those steps is the logic, explanation, and reasoning that makes them hold together as a narrative. If you don't understand why you're doing the next step, then all you can do is memorize it. And brute force memorization is always the red flag in a math class for when you're about to hit the wall. Okay? If you start to rely on, I'll just memorize this process. I don't understand it, but I'm going to memorize it. you are almost certainly about to experience a great deal of frustration when you're tested on something, because it's impossible. It is really impossible to keep procedures straight if you don't understand under what circumstances or why they're used. So I really do want you to have a collection of narratives instead of a collection of algorithms, because computers can memorize algorithms. We really can't, at least not without the kind of practice that would consume a lot of your time. Humans are good at remembering a story. They're good at remembering a logical sequence of events. So I'm trying to make these procedures into a logical sequence of events. That's why we spent so much freaking time right now doing the standard deviation formula, which I just could have given you and we could have been done in 10 seconds. Okay, so this is the example of my philosophy, teaching style, approach, whatever. Right now you've seen it. Once we have a standard deviation, I want to use it in a way that will actually help us understand something even more about the numbers in our data set. All right. The standard score is one of the first applications of the standard deviation. Even so, when you have a standard deviation, that is something that's useful. But the thing is, a standard deviation is still expressed in the units in which you measured your variable. All right. So if I have a whole bunch of people and I measure how tall they are, my standard deviation is going to be expressed in inches. If I take weight, my standard deviation is going to be expressed in pounds. When in my data set, if I was measuring apples, my standard deviation is going to be expressed in the number of apples. So what I would really like to do is have something that is not tied to the units in which I'd measured that would tell me how much an individual observation is above or below the average or typical or representative value in the data set. Okay. Are they a high member of the data set? Are they a lower member of the data set? That's something that I would like to know. So you've got this concept in your head intuitively already. We're just going to link it up with a mathematical construct. A new measure. Here's my little example. A new measure has just been invented that gets your worth as a member of the undergraduate community. All right. Administrations love to measure things. They love to pretend like they've got data on even vague concepts. And so we're calling this the captain's capacity. I'm sure that's the kind of thing that they would call it. But the captain's capacity has a mean of 50 points. Okay. The mean score among CNU students on the captain's capacity measure is 50. You have scored a 60. One thing we already know, you're above average. Good. Okay, great. But the thing is, we don't know how much above average you are. And the answer could be, you're 10 points above average. You just said so. You got a 60, they got a 50, 10 points. What the heck? But the thing is, we have no idea how relevant those 10 points are until we can figure out how much of a deviation 10 points is compared to other typical deviations from the mean. So, two possibilities. What if I said that the standard deviation for captain's capacity was 20 points? Contrast that with, what if I said the standard deviation of captain's capacity was 5 points? Under which of those circumstances is your score of 60 more impressive? Correct. Correct. It is more impressive if the standard deviation is 5 points and you're 10 points above than if the standard deviation is 20 points and you're 10 points above. Okay. And the reason is because if the standard deviation is 20 points, your score is only a half the standard deviation above the mean. But if the standard deviation is 5, your 10 points represent 2 standard deviations above the mean. That is to say, you differ from the mean twice as much as the typical person. What we're talking about already, without even really trying, is what's known as a standard score. The first standard score that we're going to deal with is called the z-score. The z-score is a standard score that counts the number of standard deviations away from the mean for any value. So when I said that you were a half a standard deviation above the mean, if you were 60 compared to an average of 50 with a standard deviation of 20 points, what I was really saying is that you've got a z-score of 0.5. Under the other circumstance, when you were 2 standard deviations above the mean, you had a z-score of 2. All right. The nice thing about this is that it does not rely on units, it does not rely on the mean, and it does not even rely on the variability. All those things get mixed in, but when I give you a standard score, I have baked all those things into the calculation, and your standard score doesn't actually rely on any of them anymore. So if I say, hey, I got a z-score of 2.5, no matter what it is that I've been measured on, you know that I am really, really way above the mean on whatever that thing was that was measured. Okay, no matter what the mean actually is, no matter what the variability in that population, and no matter what the units, you know that I am kicking butt if the high score is a good thing. Okay, if it's running and I say, hey, my time is 2 standard deviations above the mean, you aren't doing well because that's not good, but you get the point. I love it when I tell you that you got the point. It's really my way of comforting myself to think that, everything's okay, because I think I've gotten the point across. But anyway, here's a formula. Okay, formulas are always nice. They're nice and grounded. If you want to calculate the number of standard deviations above or below the mean that an individual observation is, you can put it into this formula. You will get out of it a z-score. So the result will be a z. So z equals the value that you're wondering about, say your score, minus the mu of the population, that is the average value of what's going on in the data set, divided by the sigma of the population. That is to say, one standard deviation in that population. You can take a look at that and realize that what you'll get when you put those numbers into a formula is a count of how many standard deviations above or below. So let's see, you can run a mile in 8 minutes, 30 seconds. That is your individual X value, 8.5, 8 minutes and a half a minute, 8.5 minutes. The mean in this example is 9 minutes. If the standard deviation for mile running is 1 minute, what would your z-score actually be? So just stuff it into the formula, see what pops out. Correct. Yeah, X is actually 8.5, not 8.3. Sorry, I misunderstood that that question. But yeah, so the standard deviation here is going to be negative 0.5. Sorry, the z-score here is going to be negative 0.5. The standard deviation was 1 minute. That means that you are 1/2 of a standard deviation below the mean on your score. Now, it turns out that given the context here, that's a good thing. The more negative your number, the better a runner you are. But it points out that it's really important to get the order of things in the numerator here correct, because negatives and positives are exceedingly meaningful when it comes to standard scores. If you have a negative z-score, that means that you are counting standard deviations below the mean. If you have a positive z-score, you are counting standard deviations above the mean. All right, this is one of those times when it makes a whole lot of difference and you need to keep track. All right, that is the end of chapter 2. I let it go at z-scores, and we are now going to be ready to do the in-class assignment that we have on Friday, which is going to be doing a standard deviation with your group. Is it complicated? It is not. Will it take a whole lot of time? It should not. But I'm going to be leaving you time after all installing SPSS together to kind of luxuriously have the time necessary in order to get to meet your group, work out any kinks, and solve the problem with plenty of time left. Okay. Before we do that, it's important for me to get across to you what I expect in terms of giving answers in this class for interval or ratio variables. Significant figures.
Niehaus?
Yes.
Sorry, can you go back to the formula for z-scores, and can you explain where the numbers go in the formula?
Sure. Let's take a look at that just real quick. Find it, pull it back up. Oop, gotta share that. Hold on. So for the little example that I was talking about with running, all right,
Yeah.
you've got 8 minutes and 30 seconds, which means 8.5 minutes. Correct? Okay. So 8.5 is your X value. That's the individual observation that you're dealing with. So in this formula, 8.5 would go right here for X. The mean of the entire population of runners is 9. So you would have 8.5 minus 9. It's important, as I said, to get these in order, because if the mean is bigger than your score, you're below the mean, you're going to get a negative value. If the mean is smaller than your score, this subtraction will give you a positive value, and you're going to be working with something that's above the mean, right? But in this case, 8.5 minus 9 on the top then gets divided by the value of a standard deviation on the bottom, which conveniently enough is 1 minute. And so we just stick with the negative 0.5. The z-score here was negative 0.5. In a situation where you have an 8.5 minute time, the average is 9, and a standard deviation is 1, your 8.5 minutes is half a standard deviation below the mean. Half a standard deviation below the mean is a z-score of negative 1/2, negative 0.5. Is that what you were after? Is that the explanation that
Yes, thank you.
makes it work? Okay, great. So we swap back to significant figures then, and significant figures is our way of keeping ourselves humble when it comes time to report values. The reason why significant figures are important is because we don't want to let people claim extreme precision where none exists. All right. If I say that the length of my street is 350 yards, 17.87653 inches, you would be like, wow, what do you have to measure that street? Because you certainly didn't walk it off with your feet, assuming that it's about 12 inches a foot. You must have had some electron microscope kind of distance projection device that is really impressive. Can I see it? Right? To say that I've measured something with that kind of precision would then essentially be a lie. And we do not want to get ourselves into a position where we are lying. So we have to worry about significant figures. It also nicely standardizes answers so that it's easier to know that we're all giving the right answer on an exam. Okay. So added a little bonus for me. But here are some rules. Here are the rules for doing significant figures in this class. Your significant figures are always based on the precision of the raw data that you collected in the first place. Let's give an example. I was measuring something in length in centimeters, okay? The first measurement I had was 1.12, the second was 1.34, the third was 2.31, the fourth was 1.8, and the last one was 2.321. Here's the thing. Those raw measurements are what determines how precise my conclusions are, no matter what I do with those numbers. Okay? Take a look at this fourth measurement here, 1.8. That means I don't really know where in the 1.8 centimeter range I was above or below 1.8. This would cover the whole range between 1.75 and 1.85, or 1.84 probably. So I don't know whether the reality of this measurement was 1.75, 1.84, or anywhere in between. That means that the sum of all these numbers is still going to have a range of 1/10 of a millimeter around the answer, no matter how precise the other measurements actually are. There's still going to be a doubt by virtue of the fact that this could have been anything between 1.75 and 1.84. So the least precise measurement in your raw data is the limiting factor for how much precision you can claim at the end of the day. All right, so your benchmark here is going to be that 1.8. Now, if for some reason I fail to give you or talk to you about what the raw data was on an assignment or a test, always assume that we're talking about whole numbers. Okay, psychological data usually starts off in whole numbers in a way that this is not. All right, once you know what your limiting measurement is, there are some rules to how you use it when you're putting it through the formulas, when you're putting it through the paces. Those rules concern two different expressions of a number that you're working with. One is a calculated value, and the other is a reported value. Calculated values do not get rounded, okay? If you're doing a value in the middle of your procedure, in the middle of your calculations, take it out to as many decimal places as your calculator or your paper can handle. At least 5 past the benchmark measurement from your raw data set, okay? You can pretend for the time being that you have incredibly precise instruments until you get to the end and then be honest in your report. So when you're doing a calculated value, don't worry about rounding. I call it calculated value because what this means is that you're in the middle of your calculations when you do it. But the next thing is the reported value. When you go public with your results, when you put it on the answer line for me in an exam, or you put it on the answer line for an in-class assignment, that's when you need to clean it up and be honest about how much precision you had in your raw data before you started doing your calculating. All right. When you do a reported value, that's for public consumption. The thing that I need you to remember, though, is that if you take that reported value and you start doing calculations with it again, don't use the rounded value. Use the calculated value that was super long and precise. All right? You only ever apply the rules of significant figures at the end of what you're doing. And if you decide for that thing that you reported not to be the end, then you pick it back up, expand it back to calculated values, and then keep going. So you might have in a procedure 4, 5, or 6 reported values as I check in on you for every step of the way. At every one of those steps, you would shorten or round for reported value, put it out there on the answer line, and then if you take that value back into the procedure, you would then revert to the calculated value, do some more things, put it on the line as a reported value, and then add precision or add decimal places back to do the next thing, and then do that as many times as necessary. If you are adding and subtracting a number, then you would round to exactly as much precision as you had in the raw data. So in the example that I had here, where your measurement was 1.8, if you're adding all those numbers together, you would get a sum, but then you would express it to 1 decimal place because you only had 1 decimal place worth of precision in your raw data. No matter what number you got, you would round to the 10th place, okay? 1 decimal place. That's for adding and subtracting. But we are very rarely going to do any procedure that ends with addition or subtraction. We're almost always going to be squaring, which is a multiplication, or taking a square root, which counts as a division, or doing division, which is a multiplication as well. So anytime you multiply or divide, you buy a one-time extension of precision by 2 decimal places past your least precise raw data measurement. What do I mean by one time? What I mean is that if you have a multiplication or division or a square root anywhere in your procedure, your reported value can go 2 decimal places past the least precise measurement in your raw data. It does not matter how many times you multiply. Okay? If you multiply twice, you don't suddenly get 4 decimal places of precision. You multiply 3 times, you get 6 decimal places. No, 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 no. If you do anything like this, even once in your procedure, you get to add on 2 decimal places to your answer, and that's all that you get for the rest of the time. Okay? That is to keep us that's to give us some credit for the idea that when you divide things, you sometimes want to slip a value in between what you could measure, because like 1 plus 2 is 3, but the average of 1 and 2 is 1.5. If I was forced to round back, I would have to say something like the average of 1 and 2, the arithmetic mean of 1 and 2 is 2, because I get a 1.5 and then it round to a 2. We do want to be able to shoot the gaps just a little bit by giving ourselves a little bit more precision than we started with, but only if you do a multiplication division, okay? And so let me hold on. I'm going to go back and put that presentation back up. All right. So let's say that our raw data gave us a mean of like what is to have here in the slide. And for example, 5.3333 repeating, that's a third. Anytime you divide something, you have a third hanging off, it's going to show up in your calculator as 0.3. If your raw data was in whole numbers, your reported value is going to be 5.33. Okay, 2 decimal places past the raw data, which was in whole numbers. But if I took 5.3 and multiplied it by 2, I do not suddenly get to report 6.6666 and have 4 decimal places. Doesn't work. I'm still going to be restricted to 2 decimal places because my raw data was in whole numbers and I did as many multiplications and divisions as I wanted. Okay, you only ever get 2. Does that make sense? Look, here's the upshot. Here's what actually happens. 9 times out of 10, 95 times out of 100, you are going to be reporting a value to 2 decimal places, because it's almost always going to be the case that your raw data was whole numbers, and you're almost always going to have done a multiplication or a division. So if you can't remember any of these other rules, put down an answer to 2 decimal places, and you are almost always going to get it right. Okay. Yeah. And that's what we got. So significant figures almost always boils down to use 2 decimal places. But it also boils down to, if you have rounded your number and then you go back into your procedure and use it to go further, unround it for use and then round it again when you make it a new answer. Okay? So those are our little rules. On Thursday, we'll get back together. I will walk you through the steps that are necessary to install SPSS on your computer. Once we get that done, people will go and break out into their Google Meet separate rooms and do the in-class assignment together. There'll be a PDF that is up on the Scholar page that everybody can simultaneously look at, download, print out, whatever. You will confer with each other on your own little 5 or 6 person Google Meet channel, get consensus on what the answers are going to be, and then one person will turn in either a scan or an image of the answers you came up with, so that I can grade that for your whole group and give you all the same grade. Okay. There will also be a way to indicate who it was that participated in that group project, so that only those people get credit for having done that. So come back into the main chat, to the main Google Meet chat on Thursday at 11, and I will let you know when we're going to break out into our other groups. Okay. By the way, if you have a roommate or somebody that you are not physically distant from, who is in this class, and it would be convenient to share one space and one camera for the purposes of doing an in-class assignment, let me know that, and I'll shuffle the groups up a little bit in order to take advantage of people who are already in the same room or in the same space to work together. Okay. All right. Any other questions before I don't go more minutes over? All right. Good to hear. Thank you all. I will see you back at 11 o'clock on Thursday.